Hi, it's Steve Chalk again. In my last video I promised I would talk about an isomorphism between Cantor's Power Set Theorem proof and his diagonal argument. We'll discuss this and a whole lot more. For people who are impatient, I'm going to start with a quick summary. Infinity is rife with paradox. Examples are everywhere. Cantor's Power Set Theorem proof and his diagonal argument, which are both intended to prove the same thesis, leverage the same paradox. They just present the paradox in different forms. So the two arguments are isomorphic, which means they have the same abstract structure. The power set theorem proof depends upon the existence of a set with a paradoxical definition under the assumption of a surjection between an infinite set and its power set. Likewise, the diagonal argument constructs a number using a paradoxical definition under the assumption of a full enumeration of reals on 0, 1. The diagonal argument and the power set theorem proof both have the same abstract structure. They both traffic in self-referential paradox in order to establish an ostensible contradiction in a proof by contradiction. Self-referential paradox is not a valid inferential tool. And I'll have to note that the diagonal argument is not generally stated as a proof by contradiction, but that's its essence. So what is an isomorphism? Isomorphism is derived from Latin and it means equal form or one structure. It describes a situation where two forms can be shown to exhibit the same abstract structure. A formal definition from Wikipedia: an isomorphism is a structure-preserving mapping between two structures of the same type that can be reversed by an inverse mapping. Isomorphism is actually a beautiful concept whereby relationships are abstracted for comparison. In the proper context, statements about one algebraic system can provide insight into another because they have the same abstract structure. I'm going to give you a few examples of isomorphisms. The general form is this. We have sets A and B and general operations star and plus on those respective sets, and they have to meet certain criteria. The squiggly equal sign is the symbol that I'm using to indicate isomorphism. I don't know if that's standard. A great example is the set of positive real numbers over the operation of multiplication and the set of logarithms of positive real numbers over the operation of addition. If a times b equals c, then the log of a plus log of b equals the log of c. In terms of mapping, we would map each number to their logarithm, and the result of a times b would map to the result of log a plus log b. The set of positive real numbers is related under multiplication exactly as the set of logarithms is related under the operation of addition. So we could say that reals on multiplication are isomorphic to the logarithm of reals on addition. How about these two infinite sets, positive integers and negative integers? We would map them 1 to negative 1, 2 to negative 2, 3 to negative 3, etc. And they're isomorphic at many different levels of detail. They're isomorphic simply because they have the same cardinality. They're also well ordered by magnitude using the absolute value. And there's a structure preserving mapping under many different operations: addition, raising to an odd exponent, etc. And note that the isomorphism does not extend to multiplication, even exponents, and many other functions. The concept of isomorphism relates to the context, level of detail, and the operations under which the sets are compared. Before we get down to the diagonal argument specifically, let's look at binary fractions and how we can describe them in terms of their abstract structure. Let's take this example. Now, what does this string of zeros and ones represent? It's a mapping of digits to negative powers of 2, whereas 0 indicates exclusion and 1 indicates inclusion. To make it easier to picture the mapping, I'll write the binary fraction vertically. Here we can see the first place maps to 2 to the negative 1, the second place 2 to the negative 2, third to 2 to the negative 3. Basically, the digit in position n maps to 2 to the negative n. We can establish a trivial structure preserving mapping from the binary fractions to natural numbers. I've omitted the binary point. So the first place maps through to 1, the second place maps through to 2, third place maps through to 3, etc. If we apply the mapping from the binary digits to natural numbers, any binary fraction can represent a subset of natural numbers. An entry of 1 in position n represents inclusion of the natural number n in the subset, whereas 0 represents exclusion. For example, an infinite number of zeros maps to the empty set because the zeros signal exclusion of all natural numbers. The number 0.1 with all zeros following maps to the subset with just the element 1, because 1 in the first position signals inclusion of the first natural number. Hence we have this relationship we see here. Now let's look at an enumeration of reals in 0, 1, and I'm going to take my example from my first diagonal argument video that's used in Cantor's argument. We'll call this enumeration the set S with members represented as S1, S2, etc. So each binary place, each column represents an element of the infinite set of negative exponents of 2, and we can map these digits to the natural numbers with 0, 1 signaling exclusionary inclusion. So our enumeration maps S to the power set of n this way. You can see S1 maps through to P1, S2 maps through to P2, S sub n maps through to P sub n, where P1, P2 through P sub n, they represent individual subsets of n, which of course are members of the power set of n. So we can map each S sub n to a subset of n. We'll call this map SP, where SP of Sn is equal to Pn. So SP is a mapping from S to the power set of n, power set of natural numbers, and if S is a complete enumeration of reals on 0, 1, then SP would be a surjection. A quick note here, the diagonal argument is essentially argument to contradiction, but it's not always presented that way. The enumeration is characterized as an arbitrary enumeration, not necessarily complete. And then D is generated to show that any arbitrary enumeration cannot be complete. But of course, this is just argument to contradiction cloaked in circumlocution, demonstrating that no arbitrary enumeration can be complete is logically the same as assuming the enumeration is complete and showing this leads to a contradiction. Here is the diagonal argument as stated as argument to contradiction. Assume S is a full enumeration of reals in 0, 1. Generate a real number D that's an element of reals in 0, 1 that is not in S, therefore S cannot be complete. The assumption that S is a full enumeration is contradicted. So with this understanding, we're going to proceed with the assumption that S is a complete enumeration. Each entry in the enumeration S can represent a subset of n, and in total the enumeration, if complete, represents the power set of n. And let's quickly observe a trivial mapping of the natural numbers to S1, S2, Sn. Combine this with a mapping function SP, and we have a compound mapping from the naturals to elements of power set of n. 1 to P1, 2 to P2, 3 to P3, etc. Let's call this compound map I, where n is an element of n and I of n is equal to Pn. If SP is a surjection, S onto P of n, then I is a surjection naturals onto the power set of n. The mapping SB establishes an isomorphism between the enumeration S and power set of natural numbers. What if we ask, what is the image of D under SP? What is SP of D? We can recognize a more complex isomorphism that includes the definition of the diagonal number D generated on that set S, and the definition of the key and paradoxical subset Cantor defines in his power set theorem proof. Using the same logic where we map the binary digits of Sn to members of natural numbers, D maps to a subset of n. Let's call it PD. So D maps to PD, and we can say that the image of D under SP is equal to PD. Now, what is the nature of PD, and how does it relate to the power set theorem proof? Well, we're going to show that PD is isomorphic to Y. Recall the set Y from the power set theorem proof. Psi is a mapping of infinite set X onto the power set of X, a surjection from X into the power set of X. Cantor defines set Y, a subset of the power set of X, an element of the power set of X thus. Y equals all X elements of X such that X is not an element of the subset that it maps to. So Y is all X such that X is not a member of the subset to which it is mapped. This subset definition is paradoxical, you can see from my videos, and Y is a subset that simply cannot exist. So how does this relate to the diagonal number D? Alright, I'm going to pull all of this stuff together now here. In Cantor's power set theorem proof, we're going to let the set X be natural numbers, so we have this definition of Y. Recall that D sub n is the diagonal number generated to n places, and little dn is the nth digit of the generated number D. and we'll let S sub n colon n equal the nth digit in the number Sn. Recall our mapping I is a mapping from natural numbers to power set of natural numbers. Now, if we're going to review Cantor's flipping procedure here, recall that the digits occurring in the diagonal are flipped in the construction of Cantor's diagonal number d. And let's recognize the same relationship between d and the elements of n as we do for members of S. D can represent a subset of n, which we'll call PD. And we're going to show that PD is isomorphic to Y. Just to keep things clear, the mapping SP of D equals PD, which is a subset of n and an element of the power set of n. So PD is an element of the power set of n. Since I is a surjection from natural numbers onto the power set of natural numbers, it follows that there is a natural number that maps to PD. We're going to call that number NP. So PD is the image of D under SP. I of NP equals PD, and D is isomorphic to PD. Let's call the nth digit of D Dn, and recall that n maps to Sn, which maps to Pn. So S sub n colon n, which is on the diagonal of S, refers to the nth digit in the member of S, which is mapped by natural number n. So now let's construct D. If S colon n is 1, n is an element of Pn, and we define D sub n equal to 0. This means that if n is a member of the subset to which it is mapped, it is not included in the subset mapped by D. If S sub n colon n is 0, n is not an element of Pn, and we define D sub n equal to 1. So if n is not a member of the subset to which it is mapped, it is included in the subset mapped by D. So now we can state this definition of PD, which is isomorphic to D, in this familiar set theory form. PD is equal to all n that are elements of natural numbers, such that n is not an element of I of n. And recall that Y equals all n elements of natural numbers, such that n is not an element of psi of n. Here we see the isomorphism stated pretty clearly. Psi maps n onto the power set of n, and Y is defined thus. I maps n onto the power set of n, and PD is defined in the same way, and it is isomorphic to D. D is isomorphic to PD, which is isomorphic to Y, so by transitive property, D is isomorphic to Y. The two methods of proof utilize the same abstract structure, so the two arguments are isomorphic. So what are the implications of this isomorphism? The two methods of proof utilize the same abstract concept. So in essence, the diagonal argument used ostensibly to prove that there are more reals than naturals is isomorphic to Cantor's proof of the power set theorem. Recall from other videos that the power set theorem proof fails because the set Y is defined using a self-referential paradox and cannot exist. Y is paradoxical and cannot exist, hence D is paradoxical and cannot exist. The definition of D then is essentially self-referential. S is a complete enumeration of reals in 0, 1. That means that the construction of D would encounter itself as D is an element of the complete enumeration. D encounters itself in the flipping procedure, which defines D. That's self-reference. The definition of D then is self-referential. Just to be careful here, because people are always raising smart objections, intelligent objections, this statement itself is paradoxical. If D exists, then D is an element of S. But that renders the definition of D a self-referential paradox. Hence, as defined, D does not exist. So when I say D is an element of S, that itself reveals the paradox. Again, to be clear, all of the real numbers on 0, 1 of course exist. However, there can be no real number on 0, 1 that meets the definition of D. So D, under that definition, is not a number that can exist. Making this intuitive, we could simply observe that if S is a full enumeration of reals on 0, 1, then D must be a member of S. Yet the construction of D, because it is built on a relationship with all the members of S, will include itself. Under the assumption of a full enumeration, then, the definition of D is self-referential, just as the definition of the set Y is self-referential under the assumption of a surjection. Like y under the assumption of a surjection, d cannot exist under the assumption of a full enumeration. So both methods of the proof use self-reference to leverage the paradoxical nature of infinity. They are essentially the same proof down to isomorphism. So the definition of d is paradoxical, d does not exist, and the proof by contradiction depends upon the existence of the diagonal number d. Hence, the proof by contradiction has no contradiction and the proof fails. Now, I was going to do more in this video, but it's running kind of long, so I'm going to save it for another one. So I'm going to issue some clarifications of my previous diagonal argument video in a later video. Thank you.